even know if I like calculus. Yeah, you haven't seen it yet. So let's start playing with the foundation of it. Sound good? The foundation of calculus, preview of calculus. What is calculus? This is not a section in your book. This is an intro, but here's where calculus gets exciting. It's the math of change. It's dynamic. It's not static. It moves. It allows for variance. Whereas, well, actually I have examples. Let's just lead into it with that. Before calculus, you could plug in x equals c to a function and get the y. Yay. With calculus, and technically you guys have some tricks you've done this year. If you didn't realize they were tricks. With calculus, you can plug in a c even if there's a hole and say, yay, I'll still find you. Before calculus, it's like we can find slopes of lines and parabolas that are really complicated. We can find slopes of lines and parabolas, but nothing else, which means we can only find the rates of linear motion. However, with calculus, we can find the slope, we can find the rate at any point of any modeled function, not just parabolas. Before calculus, we could do secant lines. Yeah, sure, give me 2 points, I'll give you a line. With calculus, we can do tangent lines, not just to parabolas, and not using geometry. Before calculus, we could do an average rate of change, as long as we had some change in distance and some change in time. With calculus, we can say, what's going on right now at this point in time? Before calculus, we could do curvature of a circle. You guys did it in geometry. After calculus, we can do curvature of anything, any curve. Before calculus, we could figure out the height at c. Now this is interesting. Let me put it this way too. Before calculus, to find a max, you would need your calculator. After calculus, we'll find the max by hand ourselves. Colby, hang on. Before calculus, sure, we could deal with spheres and tangent planes, but after calculus, we can deal with any surface with a tangent plane. Before calculus, we can figure out direction of motion that goes along a single line, like you're right behind a box pushing it straight forward. However, with calculus, we can figure out direction of motion even if it's along a curve and not a straight line. Speaking of vectors, ooh, that was a vector. Before calculus, only work done by a constant force, but how many forces are constant? Some are. Most aren't, at least most human forces aren't. So then with calculus, we can also deal with work done by a variable force. We could deal with areas of rectangles before. After, we can deal with areas of anything, even if there's a curved side that's not circular. Before, we could find the center of a rectangle. After, we could find the center of any region. Before, we can find the length of a line. After, we can find the length of an arc. And any arc, not just a circular one. Before, we could find, sure, volume of a cylinder, memorize pi r squared times h. But after, we can find volume of some of these weird quadric surfaces, and not just the ones formed by rotating conic sections. Before, we could find mass of solid, but not of variable density. Sorry, constant, but not variable density. Before, volume of just normal geometric shapes. Sorry, that was surface area. After, volume of any irregular region that could be defined by functions. Before calculus, sum of a finite number of terms. After calculus, sum of an infinite number of terms. That's more BC. You guys learned a trick, and I showed you a limit. So technically, you've seen the calculus. Doesn't mean you understood it. Anyway, all of calculus comes down, at least the intro to calculus, to 2 problems that needed to be answered. And in answering the 2 problems, there was a whole branch of mathematics that was created. As you guys write down the picture, Colby, go. What's up? Oh, cool. Could you have written all that stuff down? Sure. Did you need to? No. And that was just the very, 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 very mathematical way of showing before and after. And that's not even applied to fields like economics, medical imaging, CGI. Physics, engineering, pharmaceutical sciences, pure and applied mathematics. But I think one of the, as far as I know, which I'm definitely not an expert, but as far as I know, one of the fields that most involves or needs calculus in the last, I think it's been 50 years. One of the fields that has grown and that has expanded to where it uses calculus more than most others would be economics, ironically enough. So in college there are courses called business calculus where calculus is only applied to business. There are also some calculus classes that have been tailored to science majors specifically, possibly for different reasons, but trying to apply it to the medical field specifically as well. There's some applications as far as efficiency as to trying to figure out the dosages for medicines to different patients based on their height, their age, their body weight, etc. Anyway, all sorts of different applications of calculus. And it all comes down to two different problems. One is called the tangent line problem, and that's what you're looking at. And we've seen a tangent line this year, and I kind of made a big deal about it, but it was kind of hard, and you guys didn't really like it. We dealt with it geometrically in a parabola. The tangent line problem says, how on earth are we supposed to find a tangent line when we only have it hitting at how many points? One. You're like, well, there are more points on the line. That's true, but we're given the curve. We're given the function. We're not necessarily given the line. And you might be like, well, we have a section for that. We're in pre-cal. We're awesome. Yeah, we're pretty good, except as soon as I do that, all of a sudden that whole section just goes out the window because it only worked for parabolas. Wouldn't work for cubics or quartics or quintics. Definitely wouldn't work for trig functions or exponential or logarithmic or rational functions, whatever this might be a piece of. So all of a sudden, what we worked so hard on for a parabola, it'd sure be nice if there was a better way of dealing with it. So the dilemma of a tangent line. How do we find the slope of the tangent line from which we can get the equation of the line if we only have 1 point? And all the way in all of your math up until this year, you were always told the only way to find a slope is rise over run, and to get the rise over the run, you need a change in over a change in, think average rate. You need a change in y over a change in x, which means you need 2 points. So here's the interesting thing. What if, with pre-cal, what if we go ahead and say, all right, a tangent line, I know that's what I'm supposed to get, but what I can actually get is a secant line. What I can actually get is, well, I can't get the tangent line using my old school math, but I can establish some other arbitrary point, a certain delta x distance away from the original point. So here's my point of tangency. Here's the point that I want the tangent line to be at. But since I can't find another point, fine, I'll pick my own other point, and I'll name it arbitrarily. C plus delta x, starting at the original x value, adding the distance to get to the new x value. And then I'll go ahead and plug in that new x value to get to a new y value. Long story short, we could choose some other point and find the line through that using rise over run, secant line. But should we be satisfied to stay here at this approximation when I really want a different line altogether? Hopefully not. So if that's not sufficient, if that's not good enough, how could I get a better approximation? And the answer is you get closer and closer and closer. And those are better, but guys, how could I do even better than this last blue line? Go even closer. Wouldn't that be a better approximation? Or go even closer, or go even closer, or go even closer, or go even closer. Would I want to go past P? No, that wouldn't make sense. But I am going to want this distance, how far apart the 2 points are, to get closer and closer and closer. Well, no, the points are getting closer. What's happening to delta x as I come in? It's getting smaller. But it's not getting smaller like towards negative infinity smaller. It's getting smaller like closer and closer to 0. Delta x is getting closer and closer to 0 because this point that's removed is getting closer and closer to the original. Do we have a word this year that we've used in pre-cal stuff that's meant getting closer and closer and closer and closer and closer? Converging has a deeper meaning because it means that you're actually converging to a set quantity, which I guess you could say, hopefully it will converge to the slope of the tangent line, but sometimes it diverges, so careful. I would use approaching. So we need this delta x to approach, what did I say again? 0. Oh. So, if we can have the delta x approach 0, asking ourselves the question, is there a, do you remember who this guy is? Limit. If I can take the limit, or if I can look for a limit as delta x approaches 0 of, wait a minute, what are we trying to do? Tangent line. What can't we do? Slope. How can I write the slope? The slope would be y2 minus y1 all over x2 minus x1. I'm plugging into an algebraic formula, y2 minus y1 over x2 minus x1. I'm taking the limit as the delta x's go to 0. If this could be solved, if it does converge to a value, guess what? I will have found the slope of my tangent line. I will have done the impossible. And there was a lot of math that went into, a lot of philosophy, to be honest, that went into whether or not this was an actual possible thing. A lot of years of history that went into discovering this. But, Eileen, who is this guy? Who is this guy? Who is this guy? Forever card. You got it.
That's the definition of the derivative.
Exactly. It's the definition of the derivative. It's f with a little baby apostrophe. We call it f prime. The parentheses c, that's just function notation of x, but of c is the definition of the derivative. The answer to the first big problem of calculus is what we would call a derivative. Now, have I fully shown you what it is? No. I've shown you the problem. The problem is we wanted a tangent line. We only had 1 point. Well, we could do the slope of the tangent line with, no, we couldn't. We could do the slope of a secant line with 2 points. But if only we use this little idea of approaching, how we make the 2 points, the arbitrary point and the point of tangency, get closer and closer and closer and closer, throw some math symbols, some math notation in to help us get the idea of cross. Now, I haven't shown you how to solve this, but it's just the idea of need to approach to get to this line. We go straight to it, at least not without shortcuts. Shortcut rules are a thing. Second problem. Number 2. First big problem, tangent line problem. How do you find the slope at 1 point? How do you find the slope at 1 point? Which has a lot of implications, a lot of applications. I gave you guys just a taste of a few of the fields and a few of the applications of calculus. So just trust me that it's super, super important. The second big problem is, how do you find the area of a non-geometric shape that could be defined by a function or a curve? Now, how would you guys think of approximating this guy? What shape does he look like that we could find the area of if we knew a and b and f of x? Any ideas? He is a cubic function, but I don't think you've ever found the area under a cubic curve before. What are some areas that you know?
Square.
Okay, squares. Rectangle is better than a square for sure, right? Could you choose the lowest point that it hits the function, and you could plug in a, so we could get a f of a? And could you find the area of that rectangle? Yeah. If you knew a and b, you could subtract and figure out how long that is, and then you could figure out how high this is and find the area of a rectangle. Okay, that'd be good, but it'd be an under approximation, right? Okay. How could we do an over approximation? Couldn't we choose the higher one? And couldn't we do b and f of b? And couldn't we use the exact same distance, but now plug in the right? So we'd have an under approximation, over approximation. What do you think we could do with those two? Yeah, maybe average them. Maybe add the two together, divide by 2. Would that be the exact area? No. Would it be close? Yeah. Thomas was like, what if you put a circle in? But as soon as you put a circle in, see how you've kind of ruined your rectangle? Oh, a half circle. Okay, maybe. You could have done a few triangles, right? You could have maybe done some rectangles. Maybe a trapezoid. Oh, that's what you were doing instead? Okay, here's the idea. Anything that you guys just said would change based on the figure that you had, right? You're like, oh, let's do a semicircle. Oh, let's do a triangle. Oh, let's do it. But it's only because you're seeing the shape. What if you had no idea what the shape looked like? And I said, what shape should you use? You're like, I don't know. Show me the picture and I'll show you what to do. Okay, so the idea is we couldn't just solve this problem just by doing whatever geometric figures sounded good to you and then you go ahead and solve with. There needed to be some sort of process, some sort of way that would let you approach any problem and not just the one that you're looking at. So let's just use rectangles. Let's just use rectangles. But let's not just use one. Let's maybe split up A to B into 4 subintervals and put 4 rectangles in. And just so that we can say it's some sort of systematic approach, let's go ahead and only hit at the left endpoints. Or maybe let's only hit at the right endpoints. Wherever we hit for one, let's hit for all of them. That way they're all acting the same way. And they're like, okay, well, that's a pretty good approximation. It's better than just the one rectangle. Probably better than even the one above and the one below and the averaging in between. They're like, okay, that's good. Well, we could do better. And how did they do better? Fit in more rectangles. It's a struggle. When the geometry gets, it's rough. But wait a minute, guys, isn't this still an approximation? Isn't there still some area that's missing? Like you have a few over and a lot that's under? So how could you get even better, even closer? 16. More rectangles. How about 16? How about 32? How about 200? How about 1,000? How about 1,000,000? What's going to happen as you fit in more and more and more and more and more rectangles? The bases, closer and closer to the curve. You're entirely right. It's going to be hopefully converging to the area. Ooh, but what's going to be happening to the, ready? Can't I call the base a little baby change in x, a little baby delta x? What's going to happen to the delta x as my rectangles get squished in more and more and more and more and more? Approaches, good word, 0. So what happens if I could take the limit as delta x approaches 0 of, let's see, what's the pre-calc? What's the before calc math that we're doing? Oh, area of a rectangle, right? Area of a rectangle, isn't that going to be base times height? Base times height put in terms of, well, the base is my little delta x. The height is going to be my little f of wherever we're hitting. So I'm going to say c sub I. I know that's awkward, but it's okay, just take it. And here's the reason why. Because we're not just doing the area of one rectangle. What are we doing? All of them. Added together? Repeated addition. We can make it a summation. We can go from I equals 1, the first rectangle, to I equals, in a sense, infinity. Technically, there are a few different ways of doing this one. We could have called this n and had the limit as n goes to infinity. We'll just leave it here for right now because we're not going to go too deep into every single piece of this. But the idea is we're going to add together all the different rectangles as the bases of the rectangles approach 0, fitting in a sense, an infinite number of rectangles. And that is what we would call an integral. The Riemann sum definition of an integral. So the first big question is answered by what we would call a derivative. And the second big question is answered by what we would call an integral. But did anybody notice anything that was the same between these two? Delta x approaching 0, and me needing to use the concept of limit notation. Limit notation is more the idea of a limit. The idea of a limit. And the notation is my little LIM with the delta x approaching 0. We can take limits of all sorts of things. And so before we ever can get into these things called derivatives and integrals, which is the main focus of calculus, we have to talk about this thing called a limit, section 12.1. Whew, we've gotten up to the beginning. No, you did. That was chapter 12 intro. I wanted you guys to have the tangent line problem and the area problem, but now new section, new side. Hopefully you didn't use more than one piece of paper on the other one. 12.1, Introduction to Limits. Tomorrow, I need you guys to have your calculators because we are going to be doing these in a very exploratory way. We're going to be starting off in a very exploratory sort of way, trying to discover how limits move and behave. And just a quick heads up, just today, we were going over the Calc AB kids on their mock exam / practice exam. There were 2 different mock exams I had to give, so then they both had 2 to go over and do corrections on. And guess what? I would say over half of the questions they got stuck on had to do with limits. Ironic. It's where you end pre-cal, it's where you start calculus, and yet at the end, right before their AP test, they still don't totally have them down. So focus on chapter 12. Could come in handy someday. The informal definition of a limit, and it's informal because there is no crazy epsilon delta proof going on up here on the board. That'd be the formal definition. The informal definition is if f of x, a function, becomes arbitrarily close, closer and closer and closer until it's basically inconsequentially close. There isn't really a way to get even closer. Arbitrarily close, close enough to some sort of single number L as x approaches a from either side. The limit of f of x as x approaches a is L. That's a paragraph. Going down below, it's formal as far as English, it's not formal as far as math, if that makes sense. It's kind of hard for you to understand since you don't really see mathematical proofs in high school unless you read your book, and even then. But that whole paragraph can be shortened into this little baby quotation mark. The limit of f of x, the limit of the y values of the function f as x approaches a is L, as long as L exists. You make that even shorter. F of x goes to L as x goes to a as long as the limit exists, or the limit as x approaches a of f of x is L as long as the limit exists. What are we going to do tomorrow? Get our calculators out, take functions, and actually approach. Because if all this crazy higher math stuff needs a limit, we got to start at the beginning and say, what's a limit? And we'll play with it tomorrow. Sound good? All right. Cool, kids. Is there homework tonight? No, not unless you want to go watch Why Calculus. You can Google it. I'm sure there are videos. Why is calculus a thing? Bye, guys.